Hello. In this video, I am going to go over some of the exercises from chapter 20, which is about electrochemistry. So we'll start out with sample exercise 20.4. We are given a redox reaction and told that this reaction is spontaneous. We have a solution containing potassium chromate in one in a beaker, and we add sulfuric acid to that, and then we have a solution of potassium iodide that's poured into another beaker. We set up the salt bridge and put in a conductor in each solution, and then set up a galvanic cell. This is similar to what we did in the lab yesterday. So once this cell is set up, it generates an electric current. And so they want us to tell the reaction that occurs at the anode, the reaction that occurs at the cathode, direction of electron migration, direction of ion migration, and the signs of the electrode. So just as a reminder, anode equals oxidation, remember an-ox, and then cathode is reduction, and we said we would say that that would be red cat. So we've got to first figure out which of these half reactions is oxidation and which half reaction is reduction. Okay, so in order to determine the oxidation and reduction for our ions here, let's first get our oxidation numbers. So to start here, in this ion, the chromate ion, we know that oxygen is always -2, right? And we have 7 of those. So oxygen is sitting at a -14. We have a charge of 2- here, which means that we stay at a -2 charge. So then, looking at, okay, so oxygen is at -14, we're going to stay at 2 negatives, so then chromate needs to be -12, or needs to be +12, because +12 minus 14 gives us a -2. So chromate needs to be 12. I have 2 of them, so I know that this chromate has to be +6. Okay. Now over here, this chromate I already know is +3. So I've gone from +6 to +3. In order to do that, the chromate has gained electrons. It's become closer to 0 on the positive side, so it has gained electrons, and reduction is gained. So the chromate ion is being reduced, and so this is going to be our cathode. So that must mean that our iodine is being oxidized, but let's just double check this. So we know that this iodine has a charge of -1, and this is essentially elemental iodine here, and all elemental atoms carry a oxidation number of 0. So the iodine has lost electrons. So then that means it is oxidized. So it is our anode. So we've solved the first 2 things where they ask us the reaction occurring at the anode and the reaction at the cathode. So we've done that. So now we've got to figure out the direction of electron migration. Well, the iodine lost the electrons, the chromate gained the electrons. So our electrons migrate from the iodine to the chromate. So it's not enough could just say, oh, well, the electrons migrate from the iodine to the chromate. Where is the iodine coming from? Well, the iodine is coming from the potassium iodide solution. So we can say that it's going from Ki to the solution of potassium chromate and sulfuric acid. So the electrons are migrating from the potassium iodide solution to the potassium chromate and sulfuric acid solution. Okay. Now, they also asked us the direction of the direction of ion migration. So what is our direction of ion migration? Well, in general, we can say cations, which are positive, move toward the cathode, and anions, which are negative, move toward the anion. Okay, and that kind of helps keep you straight here. Cations move towards the cathode, anions move toward the anode. Okay, and so that tells us the direction of ion migration. And then the last thing it wants to know are what are the signs of the electrodes? Okay, so what are the signs of the electrodes? Well, the anode is going to be negative, okay, because the anions are moving toward the anode. So our anode is negative, and then our cathode is positive, right? So in order to solve all of this, the first thing you have to do is get your half reactions, and that's going to help you determine which one is being reduced, which one is being oxidized, and you can move forward. In this next section, we're going to take a look at some problems using a particular reaction or a particular equation. This equation is in your book on page 869, but this is looking at the standard cell potential of a voltaic cell. And this is the formula that we're going to use for that. Okay. Remember, we talked about the degree sign being the standard. So we have the standard cell potential is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. Now, you can find the standard reduction potentials in your book on page 871 in table 20.1. They are also in Appendix E, and you can find them online also just by Googling. So in this first one, they've given us our voltaic cell with zinc and copper. This is the exact one that we looked at in class yesterday when we did our galvanic cell. So we've got to figure out what is our standard cell potential. So we're given the E cell value. Okay, so they're giving us our standard reduction potential there. They've told us our standard reduction potential of zinc, and they want us to calculate the one for copper. Okay, now they don't tell us here which is the anode and which is the cathode. So we kind of have to figure out which one is the cathode and which one is the anode. So when we look at our overall equation and we kind of look at our half equation here, we can see that copper here is gaining electrons. We have to give it electrons to get to that standard elemental state. Okay, so if we go back up to our overall equation and put in some oxidation numbers up here, we can see that we had to give some electrons to copper in order to get it to that state. And then zinc here, we see lost electrons because it went from 0 and now it's at positive 2. So zinc, in its loss of electrons, zinc is going to be oxidized, and so it is the anode. And copper, by gaining, is going to be reduced, so it is our cathode. Okay. So what we're trying to solve for then is our cathode value. So we'll rearrange our equation to solve for the cathode. And so that would be E cell, and we're moving this to the opposite side. So plus our reduction potential of our anode is going to be equal to reduction potential of our cathode. Okay, so we have 1.10, that gave us that, plus this is a negative 0.76, and so that's going to equal 0.34 volts for our reduction potential of our cathode. And we can double check this because we can look in table 20.1 and we see that indeed the reduction potential of copper 2 plus to copper is 0.34. And of course that would be positive. Okay. So now we have a different example of using this equation. We've got the same cell that we just looked at in exercise 4, and they want us to calculate our standard cell potential. They did not give us any information here, so we're going to have to figure out, just like we did in the first one, what's our cathode, what's our anode, and get our values for those. So looking back at example 20.4 that we just looked at, we saw in this example that chromate was reduced and that the iodine was oxidized. So we're going to use that to help us solve this equation. So the chromate is reduced. Okay. And so that makes it the cathode. When we look over on table 20.1 and we find chromate, we see that for chromate, its value is plus 1.33 volts. So then that means that our iodine is oxidized, it is our anode, and when I look at the value for it over on the table, I see that it is plus 0.54. So now I plug this in. I have my cathode, which is 1.33 volts, minus my anode, which is 0.54 volts. And so that's going to equal a positive 0.79 volts. Okay, so that's my answer for this one. So we had to work this one a little differently, but still had to determine our cathode and our anode. Now, one thing I want you to pay attention to here is when we have the reduction of the chromate and the oxidation of the ion, you'll notice that we have some coefficients here. The coefficients are important when we're balancing atoms, when we're balancing total charge, but we do not use coefficients when calculating our standard cell potential. All right. There are no coefficients. We don't multiply by anything. We just strictly go based on our standard values from table 20.1. So just watch out for that. Our next question, still digging into this equation, but a little bit differently here. So they give us our voltaic cell, and they provide us just with the half reaction here. And we're going to use the data in Appendix E, or Table 20.1, to determine which of these is occurring at the cathode and which is occurring at the anode, and then to calculate our standard cell potential. So the way that this is set up, you think, well, I mean, they're both gaining electrons, right? Well, that is how it looks. But remember, these are always reversible. So they kind of tried to trick us here. We really have to get to the bottom of which one is oxidized and which one is reduced. So I went to the appendix and I pulled up our standard potentials here. So for the cadmium, it is negative 0.403. And for the tin, it is negative 0.136. So the one for tin is less negative than the one for cadmium. So it is the one that is reduced. Okay. So our tin is going to be reduced, which means our cadmium is going to be oxidized. So let me kind of talk through that again. They're both negative, okay? This one, the 10, is closer to 0. So it is the one that is most likely to happen, because when you look at Appendix E or you look at Table 20.1, what you're looking at is the potential to be reduced. So positive values are going to be, they're going to have more of a potential to be reduced. When you have ones that are both negative, you have to look which one is the closest to 0. And it would be this one. And so it is going to be reduced. So with it being reduced, remember that equals our cathode. The cadmium then will be our anode. And so we come back to our formula, which is cathode minus anode. So here's our cathode. So 0 and it's negative 0.136 minus our 0.403, and that's going to equal positive 0.267 volts. So we've figured out our standard cell potential, and we've determined which reaction occurred at the cathode and which occurred at the anode. So if we wanted to be technical about this, and they did say which half reaction occurs, so what they're really meaning there is for us to rewrite the half reaction. So this one stays as it is because it is the one that is being reduced. But what we would do is flip around our cadmium. So basically we would need to flip this arrow, or we would rewrite it like this. Because it is our anode, it is the one that's being oxidized. Our next question here asks us to rank ions in order of increasing strength as oxidizing agents. So we're still going to use Table 20.1, but we also have a nice graphic in the book, figure 20.11. I put these in your notes for you on page 875 that helps us look at the strength of oxidizing and reducing agents. So we have our list here. We have the nitrate ion, silver ion, and the chromate ion, and we need to figure out their strength as oxidizing agents. So I'm going to look up their cell potential or their reduction potential values. And I've looked those up, and here is what we have. So those are our standard reduction potential votes. So the more readily an ion is reduced, meaning the more positive its reduction potential, the stronger it is as an oxidizing agent. All right, I'm going to say that again. The more readily an ion is reduced, in other words, the more positive its reduction potential value, the stronger it is as an oxidizing agent. Okay. So when we look here, we see all of them are positive, but we're looking at the more positive. So the highest possible value is going to be the chromate ion. The least is silver, and it asks us to rank these in order of increasing strength. So silver is the least, nitrate in the middle, and then the chromate ion is the strongest. So when you have a question like this, just look at their reduction potential. Okay. The more positive the reduction potential value, the better it is or the stronger it is as an oxidizing agent. Okay. Number 9. Number 9 wants us to use table 20.1 to determine if the following reactions are spontaneous. So we're coming back to the idea of spontaneous reactions, looking at Gibbs free energy. And we need to figure out, are they spontaneous or not? So the first thing we have to do to solve this problem is to get our half reactions. All right, so I'm going to start with A here. And when I get my half reactions for A, I have copper into the copper ion, and I have the hydrogen ion into hydrogen gas. So those are my 2 half reactions. I need to look at my oxidation, or my reduction potential here. So I've got to get my oxidation number. So I go from 0 to +2. I go from +1 to 0. So my copper has lost electrons, so it is oxidized. Hydrogen has gained electrons, so it is reduced. So then I plug that into my formula. Now, when we use this, when we're trying to determine spontaneity, we use the same formula, but we don't call it cathode and anode like we have been. It's the reduction process minus the oxidation process. Okay, so reduction process minus oxidation process. So we're going to have this. So which one is being reduced? Well, my hydrogen has been reduced, and when I look at table 20.1, I see my value on that is 0 volts. And then when I look at the copper reaction, I see that it is 0.34 volts. So my answer here is negative 0.34 volts, which means it is not spontaneous. When you have a negative value, it is not spontaneous. All right. Now let's look at our other one. Part B here. We have Cl2 gas going to the chloride ion, and the iodide ion going to solid iodine. So looking at our oxidation numbers, this would be 0, -1. So it has gained electrons, which means that it is produced. And we go from -1 to 0. It has lost electrons, so it is oxidized. So it's our reduced minus oxidized. So I get my value for chlorine, and that is positive 1.36 volts minus 0.54 volts for the iodine, and that gives us a positive 0.82 volts. So this one is spontaneous because it is positive. Okay, so you work it out the same way. Negative value, not spontaneous. Positive value. In sample exercise 20.10, we are looking at a new formula. We're reworking our Gibbs free energy formula and including a new constant F called the Faraday constant that it was developed by Michael Faraday. And the Faraday constant is equal to 96,485 coulombs per mole, which is equal to 96,485 joules per volt mole. It is the quantity of the electrical charge in 1 mole of electrons. So by having the Faraday constant, we can figure out basically how much electrical current that we have, and then we can continue to kind of rework this and plug in different pieces of equations where we can end up with figuring out our equilibrium constant and our standard free energy change for the redox reaction. So we're given this redox reaction, and they want us to calculate delta G and K for the first one. And then we've got another reaction, which is just this first one, taking 1/2 of that. And they want us to determine our cell potential, change in Gibbs free energy, and our equilibrium constant. So we're going to have to do several formulas here to figure all of this out. So the first thing we have to do is, for part A, is we need to figure out what are our reduction potential values, because we see that we need that in this first equation that's listed up here. So I'm going to start working here with A, and I need to figure out what's being oxidized and what's being reduced. So I'm going to write my half reactions. And let's get our oxidation numbers. For silver, I go from 0 to +1, and for oxygen, I go from 0 to -2. So that tells me here that silver lost electrons, so it is going to be oxidized, and the oxygen gained, so it is going to be reduced. And my values from table 20.1 give me these values. All right, so those are my values. And just like before, we're going to use that same formula, reduction minus oxidation. So I have positive 1.23 volts minus positive 0.80 volts gives me positive 0.43 volts for my, well, I don't put E cell, let's put E there. That is my cell potential. Okay, so now I'm going to use this top equation here, plug in my cell reduction. I know Faraday's Faraday value here is a constant. N refers to the number of electrons transferred. So let's get our formula set up here. So how many electrons were transferred? Well, I have to go back up here and look to see how many were transferred. Well, I have 4 silver here, 4 silver here, which means I've got a +4 value. I have a -2 here, 2 there, so -4. And remember, these have to balance. So I've got -4, +4. Well, that has to mean that 4 total electrons were transferred. Okay, so I'm going to plug in -4. Then I'm going to put in my Faraday value. And then plug in my cell potential here. Now, the volts will cancel. And when I do the math, I have negative 1.7 times 10 to the 5 joules per mole. Okay. And that we know is our unit for Gibbs free energy. So my change in free energy here is negative 1.7 times 10 to the 5 joules per mole. Now, we're not done because they also asked us to calculate the equilibrium constant. So we're going to use this formula right here that we saw in chapter 19 to calculate our equilibrium constant. And remember, this E value here comes from the reverse natural log. So when I put this in, I'm going to have E to the negative, and then I'm going to open a parentheses here to get all this in here. So 1.7 times 10 to the 5 joule per mole. That's my free energy change that I just had. And I'm going to divide that by R, which we know is the constant, 8.314 joules per mole Kelvin. And they told me that my temperature here was 298 Kelvin. So my Kelvin will cancel out, my moles cancel out, my joules cancel out, and that makes sense because we don't have any values on the equilibrium constant. So when I work all that out, this is what I get. 9.3 times 10 to the 29 will be my equilibrium constant. So this was quite a bit. Since this is a large number, negative 1.7 times 10 to the 5, then this tells us that this reaction is very favorably thermodynamically, so we would expect a really high number here, which we got, 9.3 times 10 to the 29. Now, I will say this. These values right here are very sensitive. I use the book value, but if you were to go to like decimals here and say you had 68.5 or something, this number would be similar, but it would be different. So when you work these out, make sure that you show me your work so that I can see exactly what you're doing here to know if this answer is correct, if it doesn't match mine. Okay, so moving on to part B, they want to know our cell potential, change in free energy, and equilibrium constant when we write the reaction this way, which is, I put a little note here, 1/2 of what the reaction is in part A. So first things first, our cell potential doesn't change. Because remember, I told you that it does not depend on stoichiometry. We don't pay any attention to the coefficient. So the value that we calculated here is going to be the same. So it does not change. Okay. Now, delta G will, because delta G is now going to be half of what it was before. You're like, well, how do you know that? Well, remember, with delta G, we put in the number of electrons that were transferred. Since this is 1/2 of the reaction in part A, I have 2 electrons being transferred instead of 4. So my delta G is going to be 1/2 of the value that I got. So it will be negative 8.3 times 10 to the 4 joules per mole. However, the equilibrium constant is not that easy. We're going to have to recalculate the entire equilibrium constant because our value of delta G changed. So I'm going to plug in my new value of delta G. Everything else is the same. And that gives us 3.5 times 10 to the 14. Okay. So that is our standard potential, change in Gibbs free energy, and equilibrium constant. So we had a little bit of work saved for us with these two, but then you do still have to work this one out completely. Okay, so now we're going to move on to exercise 20.11. 20.11 wants us to calculate EMF. And we have a new equation that we use for EMF. Now, what we're looking at here is when we have cell potentials that are under non-standard conditions. And we use the Nernst equation for that. And page 880 in your book kind of goes through this entire process of how we extract the Nernst equation. But it is E, which is the same as EMF, okay? And that is equal to our standard potential minus 0.0592 volts over N log Q. And we're taking in, we're using our delta G that we just looked at that was equal to a negative FE and plugging that in and then kind of continuing on instead of the natural log, putting in the base 10 log, and this ends up being our equation. So we've got our standard cell potential minus 0.0592 volts divided by N, which is going to be our electrons. And then Q, log Q, and Q is our reaction quotient that we looked at back in 19. So the first thing I need to do is solve for Q. When I solve for Q, I'm going to go back to my original equation up here. So Q is equal to the concentration of the product divided by the concentration of the reactants. And we only put in aqueous solutions in this case. So we won't consider the iodine and we won't consider the water. So our only product will be our chromium ion. And remember, stoichiometry does come into play for this. We raise it to the power of the coefficient. So I'm going to raise that to the power of 2. And then I'm going to put my reactants in here. I see iodine has a 6 in front of it, so I raise it to the power of 6. I put in my chromate. There is no coefficient here, so I understand that to be 1. And then my hydrogen I see is 14. So then I'm going to plug in my values for that. So they told me what my concentrations were here. I plug in chromate on the top, and that is squared. And then iodine is 1.0 molar, the chromium 2.0 molar, and the hydrogen 1.0 molar. Now, 1 to the 6th power is still 1. 1 to the 14th power is still 1. So what I have on the bottom is 2. So I need to figure this out, divide it by 2, and when I do that, I get 5.0 times 10 to the negative 11. Of course, all of my m's cancel out there. I don't have a unit. It's 5.0 times 10 to the negative 11. All right, so I've got my Q. So I've figured this out. I need to figure out my standard cell potential there, or my standard potential. So this is reduction minus oxidation. So I need to look up here and figure out which one is reduced and which one is oxidized. Well, this is the same one that we did all the way back in 20.4. And we said that the chromate was reduced and the iodine was oxidized. So when I plug that into my cell potential formula, I get plus 1.33 minus 0.54, and that gives me plus 0.79 volts. So now I have my cell potential. I've got Q. I've got to look at N. How many electrons were transferred? Well, let me go back up here to my original one. I know that I'm dealing with the iodine and the chromate. This is -6. This is +6. So that tells me that I had to have 6 electrons being transferred. So my N is equal to 6. So let's plug this in. So EMF is equal to positive 0.79 volts minus 0.0592 volts divided by 6 log of Q, which is 5.0 times 10 to the negative 11. And when I do all the math, I get 0.89 volts. So that is my EMF at 298K when I have changed my concentrations of each of my, or of some of my. In our next sample exercise, we're still going to use the Nernst equation, but we're going to approach it a little bit differently. They give us the cell potential, or the reduction potential here, is 0.45 volts at 25 degrees Celsius. They give us the concentration of zinc, 1.0 molar. They give us the pH 2, which is 1.0 atmospheres, and they want to know the pH of the cathode solution. So we're going to put some things together from our previous few chapters here. So we're given a description of our voltaic cell. They tell us it's the one that's like figure 20.9. We have our EMF, or it's our E, our EMF value, 0.45 volts. We have the concentration of zinc. We have the partial pressure of hydrogen gas. We need to calculate pH. Well, how do we calculate pH? Well, in order to get pH, we have to first get to the hydrogen ion concentration. Once we have that, then we know that pH is negative log of that hydrogen ion concentration. So really what we're being asked here is, how do we get to the hydrogen ion concentration? So we've got to figure out a few things. We know we're going to be using the Nernst equation because we've got a non-standard situation. They've given us an EMF value. We have concentration, we have partial pressure. So we're going to have to use the Nernst equation, but kind of work backwards. So first thing we need to do is figure out our standard potential. Well, when we look at the reaction that is given to us here, it looks like this. So hydrogen went from a +1 to a 0. Zinc went from 0 to +2. So hydrogen gained an electron. It is reduced. So remember, this formula is reduced or reduction process minus oxidation process. So I know that the hydrogen has been reduced. This value is 0 volts. And I know that zinc here was oxidized, and its value is 0.76, but that's negative. So we know a negative of a negative is a positive, so our value here is 0.76 volts. Okay, and I just went to table 20.1 to figure that out. So I've got that. I need my N value, how many electrons were lost or gained. Well, we can see here that it was 2, because I go from a 0 to a +2. I'm at a +1, so I know I have to be at that has to be +2 there. So N is going to be equal to 2. So I plug into my Nernst equation, that's right up here. I'm going to plug in here. So they gave me the EMF, and that is 0.45 volts is equal to, I solved for my standard, that was 0.76 volts, minus 0.0592 volts divided by 2, because that's my N, that's my number of electrons that were transferred, and that is equal, or then I put in log Q. Okay, they didn't give us Q. They gave us everything else, or we figured it out. So we're going to solve for Q. So when we do all of the math here, okay, get all of this on one side and solve for Q. Q is equal to 10 to 10.5, which is equal to 3 times 10 to the 10th. You say, okay, how in the world do you do that? Well, remember to take the reverse log here. I take 10 and raise it to the power. So when I solve all of this, in order to get rid of the log, I just take 10 and raise it to the power of the value that I got when solving this first piece here. And when I take 10 to the 10.5, I get 3 times 10 to the 10. Okay, now that is my Q value, but I'm not done yet. I've got to figure out from using Q my hydrogen ion concentration. So what is Q equal to? Well, Q is going to be equal to the concentration of zinc. Remember, it's products over reactants. So I have zinc 2 plus Since hydrogen, forgot my G there, since hydrogen is a gas, we can plug in the partial pressure of the hydrogen gas, and then I divide that by my hydrogen ion concentration. And that is equal to, I just solved for 3 times 10 to the 10. Well, I need to plug in my values first. Before I put that in there. Let me plug in my values. My concentration of zinc, they told me, was 1.0 molar. They told me the partial pressure is 1.0 atmospheres. I don't know what my concentration of hydrogen is. I'm trying to figure that out. But that is equal to 3 times 10 to the 10th. And I have to, let me check my coefficients here. I have 1 zinc, I have 1 hydrogen, but I have 2 as my coefficient here, so I need to square this. So I'm going to cross multiply. And 1 times 1 is just 1. So then I divide both sides by 3.0 times 10 to the 10. No. Sorry, I keep wanting to put a 3.0 in there. So used to putting decimals, but it is just 3 times 10 to the 10. So I divide by both sides. And so that gives me 3 times 10 to the negative 11. I take the square root of both sides. And my hydrogen ion concentration is 6 times 10 to the negative 6. Remember, pH is the negative log of that. And so our pH is 5.2. So we had to kind of go around the world to solve that. But when you see problems like this, I don't want you to get frustrated or discouraged and think, how do I don't even know. There's nothing about acids and bases in here. There's nothing in here that's going to help me get to pH. But there is, because when we look back at that original formula or our original equation, we have hydrogen ions. And if we have our concentration of hydrogen ions, we can easily solve for pH. Easily, maybe not, but we can get to pH. All I had to do here was figure out my reduction potential. They gave me this value. I had to determine that my N was 2, solve for Q, plug in what is known for Q, and solve for what isn't, which was our hydrogen ion concentration. And when we got that, then we plugged it in. Sample exercise 20.13 also asks us to calculate pH. But this one is a little different. We're going to have to jump through a few more hoops to determine this. So they tell us that we have a voltaic cell constructed with 2 hydrogen electrodes. Electrode 1 has a partial pressure of hydrogen of 1.00 atmospheres and an unknown concentration of hydrogen ions. Electrode 2 is a standard in that our partial pressure is 1 atmosphere and our concentration is 1 molar. They tell us at standard temp that our measured cell potential is 0.211 volts. And we see that the electric current flows from electrode 1 through the circuit to electrode 2. And they want to know, what is the pH of the solution at electrode 1? So we're given the potential of a concentration cell. You say, what? I don't understand what that means. Well, we have a standard cell here. And then we have one that is unknown concentration. We don't know what the concentration of that one is. So we've got to do a little math here to figure out what is going to be the concentration of that cell, and from there we can determine pH. We're going to use our Nernst equation again. We're going to plug in the measured cell potential, so our EMF value, so 0.211 volts, and that's equal to, okay, that's equal to our standard potential. Well, since this is a concentration cell, this is hydrogen, that value is 0. So 0 minus 0.0592 volts over 2. Okay, well, how do I know that that's 2? Well, when we're looking at this type of concentration cell, we know that we have 2 electrons are flowing because we have 2 hydrogen electrodes. Okay, so we're going to have 2 as our N value, and that's going to be times log Q. So let's solve for log Q. Okay, so when I do all the math, I get that Q is equal to 7.4 times 10 to the negative 8. All right, so that's similar to what we did in the last problem. We had to solve for Q. We've done that. But now we've got to figure out our Q. Okay. Set up our value for Q. Well, we know that one of our hydrogen ion concentrations, the one in the standard, is 1.00 molar, but we need to figure out the other one. So electrons flow from electrode 1 to electrode 2. They told us that in the problem. So then that means electrode 1 has to be the anode. So electron 1 is the anode. Electrode 2 then would be the cathode, because that's the direction of electron travel. So we need to figure out our half reactions here. So first, in electrode 1, this is what I have. And then in electrode 2, here is my half reaction. All right. So let's kind of break this down. Like, how in the world did you figure this out? Okay. So electrical current was observed to flow from electrode 1 to electrode 2. So it's going from the anode to the cathode. Okay. We kind of talked about that in sample exercise, 20.4 that we did, or 20.3, 20.4 that we did a while ago. So electrode 1 is my anode, which means electrons are leaving, they're flowing out. Well, the only way to do that is to start with something that is 0, like I did here, and then this would be positive 1. So this was, and then the electrons leaving there, so that the electrons could go to the second one, which had to contain just the hydrogen ions, that when they were able to join with the electron, formed hydrogen gas. Okay. I know this sounds kind of confusing, but it's like, okay, but I don't understand how you knew that. Well, I knew that because I knew that electrode 1, being the anode, had to lose electrons. It was oxidized, which means it had to lose electrons. And the only way for it to lose electrons was to start in a form that had 0 here. So it had to start in its gaseous form. And in order for electrode 2 to receive those, there had to be some ions free to receive the electrons to form the gas. I know that my partial pressure of this is 1.00 atmospheres, but I don't know the concentration. That's what I'm trying to figure out. Well, in order to figure that out, I have to look at what are my reactants, what are my products, because the whole thing we're trying to figure out here now is how to use Q to solve for our hydrogen ion concentration. So I'm going to set up my Q now that I understand which ones are products and which ones are reactants. Remember, I'm trying to solve for molarity. So here's my product. So product over reactant. I don't know what it is. I assign it to X. Remember, we were doing this a couple of chapters ago. So Q is equal to X squared over 1 squared, which is just 1, right? So X squared divided by 1 is X squared. I know Q value is 7.4 times 10 to the negative 8. So I just need to take the square root of both sides, and that gives me 2.7 times 10 to the negative 4. Now, what is X? X is our hydrogen ion concentration at electrode 1. And how do we solve for pH? pH is the negative log of H. So pH is equal to 3.57. So again, don't look at this and freak out. Think I don't even know where to get started. Yes, you do. You know where to get started. They gave you your EMF value. This is a standard hydrogen, so it's got a value of 0. You know that there are 2 electrons being transferred. When we actually wrote out our equations, we can see that here. We solved for Q and got 7.4 times 10 to the negative 8. So then we had to figure out what is our Q expression. In the other one, it was a little easier. But this one, we had to develop the reactions on our own. And that's what we did by looking at the direction of electron flow. Okay, our last problem gets into determining the electrolysis and charge. So electrolysis is when we have an outside source of energy that is driving a voltaic cell reaction. So these would be like non-spontaneous reactions, and we're using electricity basically to drive that reaction. So what we've got is an electrolysis reaction. Calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10.0 amperes. So we need to figure out, when we put aluminum chloride in an electrolysis process with a current of 10 amperes, how many grams of aluminum are going to be produced by that? Okay. So how many grams of aluminum are we going to be able to separate from this molecule, aluminum chloride? So the first thing that we have to do is get this into coulombs. So remember that the Faraday constant that told us that the charge on 1 mole of electrons was 96,485, that was in coulombs. So the quantity of charge in an electrolytic cell is measured in coulombs, but they gave us amperes. Okay. So the first thing we need to do is solve for coulombs. So coulombs is equal to amperes times seconds. Okay. They told us it was 10.0 amperes. How many seconds do I have? Well, I have 1 hour. Okay. Well, there's 60 minutes in an hour, and there's 60 seconds in every minute. So there's 3,600 seconds in every hour. So that gives us a value of 3.60 times 10 to the 4th coulombs. Okay, so that was our first step, is converting amperes into coulombs. So electrical current over time, or per time, is coulombs. So we've got that. Okay, now we need to figure out, because remember the Faraday constant is the charge on 1 mole of electrons. So we need to figure out how many moles of electrons are going to pass into the cell. So let's figure that out. So moles of electron, and in order to figure this out, we're going to take our coulombs that we just solved for, 3.60 times 10 to the 4th. And we're going to say that 1 mole, we're going to use our Faraday constant and say 1 mole of electrons has the charge of 96,485 C. So when we do the math there, 3.6 times 10 to the 4th divided by 96,485, we have 0.373 moles of electrons. Okay, so we're at moles of electrons. We're not there yet. We're not at grams of aluminum. Right now, we just determined how many moles of electrons are being produced. Well, we need to figure out how many electrons are going to be released. So we need to look at our half reaction here. Well, we know aluminum as an ion has a 3+ charge, which means that it would need 3 electrons to get to elemental aluminum, which would have a oxidation state of 0. So for it's going to take 3 moles of electrons to form 1 mole of aluminum. So we can use that to figure out how many aluminums. Remember, coefficients relate to moles. So 1 mole of aluminum requires 3 moles of electrons. So we have produced 0.373 moles of electrons. And for 1 mole of aluminum, it takes 3 moles of electrons. So that means that we're going to need 0.124 moles of aluminum. So all you have to do to get to this step is set up your reaction. I'm trying to produce aluminum. What is my aluminum ion? It's aluminum 3+. How do I get there? I have to add 3 electrons. So for every 1 aluminum, I'm going to have to add 3 electrons. So 1 mole of aluminum to 3 moles of electrons. So now I need 0.124 moles of aluminum. Well, now I can use my molar mass to solve for grams of aluminum. And 1 mole of aluminum has a mass of 27.0 grams. So that gives us 3.36 grams of aluminum. So what did I do? Well, what I've done is I've calculated how much aluminum was produced in an electrolysis process. So we can do this for anything. We can do this for any type of electrolysis process. If they give us what is being electrolyzed here, what our current is, and how long we have, we can figure out the grams of anything that is going to be produced. Like your practice exercise says, how much time is needed to deposit 1 gram of chromium metal from an aqueous solution of chromium 3 chloride using a current of 1.5 amperes. So this time they gave us current, they gave us the grams, and they wanted to know time. So we could work backwards from that as well. And, kind of work each of the steps backwards to get back to time. So this is one of those that, as long as you have 3 of the 4 pieces of information, then you can calculate the next one. So I hope that this has helped you with your calculations on electrochemistry. And I'm sorry that I rambled on for so long. I didn't intend